Okay, so let's talk about when do you use what is implicit derivative and when you take explicit derivative. Um, so I'm going to talk about here if I have some type of function that just says usually that you require implicit derivative or the equation that is non-function. Do you understand which kind of equation are not function?
When like an x value has like two y values or something like that, like
no. Yes, no. Why are you so? Yes, be sure. Yes, you're right.
Oh, okay.
But what kind of test is that called?
A vertical line test?
There you go, vertical line test, right? So if you have something that failed vertical line test is not a function, but they still an equation. So for example, that if you have y equal to x squared, I can take a derivative of this. I can say dy dx is what?
Can you maximize the
Oh, my bad. Dy dx is 2x, right?
Yeah.
And we'll talk about it's a little bit more deeper than that. Is 2x, and then you say, okay, well, that's good. And some people says, well, what does dy dx mean? Because if you don't know what the dy dx mean, d stands for delta. So it'd be delta of y over delta of x, which is slope, right? Which is slope. Does that make sense? So delta y over change of dy over dx, which is change of slope. So the slope is always equal to 2x. So think about that. You can take a derivative, but the problem is this one, you take a derivative of something called explicit derivative. If you have something like this, oops, that was really bad. If something like this, you can take a derivative explicitly because a function is x squared. All I got to do is take a derivative of the power rule, which is 2x. Can you think about the same thing, but not a function?
What about like a horizontal like parabola?
Good. Horizontal parabola, it's going to be what? X equal to what? There we go. On SAT, on ACT, doesn't matter. You fail vertical line test. So it's not a function, but it's still an equation. Doesn't mean you cannot write like this. You can. It's a equation, but it's not a function because it has two outputs. Every x has two outputs. Sometimes you might have more than two outputs. So therefore, this one is not a function. Yes?
Would you have to like, could we like put a, like a restriction or something? Like, you know what I'm trying to say? Like, you know how like last, I don't know, like pre-calc when we try to find the inverse and like you have to put a restriction on like when it fails like a vertical line test. Yeah, no, never mind.
No, you're doing great. You're doing great. You technically can. So you still can do it.
Not.
I'm just trying to understand.
No, we're just intriguing about what you say. You had to be confident. Remember, that's probably going to be a future leader.
Yeah.
And you had to be. You cannot second doubt yourself. You cannot be like.
I like it when there's like feedback. Like it's when like people are like respond.
I wouldn't understand what you're saying. You're not defending.
Yeah. Yeah, you don't need a validation, okay? You are you. You don't need validate. Wait, where's Addison? Oh, she's not here. So I hear we failed vertical line test. So we failed vertical line test. We say, well, this is not a function, but it still can take a derivative. Now, there's two ways to take a derivative. We can do it explicitly. Explicitly, we can say, well, I can change this to two functions, just like what she says. You can say y equal to plus square root x and y equal to negative square root x. And I can take a derivative d to the dx here, so it'll be dy dx is equal to 1/2 x to the negative 1/2, and dy dx is equal to negative 1/2 x to the negative 1/2.
Wait.
So
Isn't it -3 over? Isn't it to the power of -3 over 2?
Isn't it?
no.
Because the one is negative.
No. It's not in the denominator.
Okay, yeah, so that's right. So
Yeah.
so you cannot do that. So you can take a derivative explicitly still, but I'm going to teach you there is a shorter way to do this, and you can take a derivative just implicitly. Okay, yes.
Why is it to the power of -1/2?
Because this one is equal to x to 1/2. You put in the front, subtract by 1. So the power subtract 1/2.
Oh, yeah. Sorry.
No, that's okay. So you still can do it explicitly. However, today we're going to show you there's another way to do this. That it's possible for me to take a derivative implicitly. So another function you can solve for y though. That requires you to solve for y, right? Can you think of any equation that is not possible to solve for y? They have to have a y.
What do you mean? Like, could you?
There's infinite amount of equation that has y in there, but you cannot solve for y. So here's a problem, right? So there's a problem. Is it possible to have an equation that you cannot solve for y? Can you think of an equation that you cannot solve for y?
If the numerator or denominator is.
That's not what I'm asking. I want you to come up with an equation where I cannot skip y by itself. It's like open-ended question. There's infinite amount of answers. You just had to come up with an example. I'm not gonna hold my breath on this one because I'm probably gonna die. Okay. So let's just think about it. How about xy minus xy squared is equal to y to the y not is equal to x squared. So is it possible to have this equation? Is it possible to solve for y here? Deborah, why are you shaking your head? Why can you not solve for y?
I don't know. I think if you wrote it down on the board under, is it possible to have an equation that you can't solve for y and you can't solve for y?
Okay, so it's it'll be a contradicting statement, right? If I create a thing, right? But the thing is, can you isolate the y here? Is it possible for you to isolate? Let's try to isolate the y. How do I isolate this y?
I mean, would it show that? Can you factor out that? Yeah. Can you factor out that? But wouldn't the x?
I can factor out an x, but it does not get y by itself. Is it possible to get y by itself? Okay, let's divide it by both sides by x, although you're not supposed to do that. But let's just assume that you can, and that's going to be x. Now, this is totally not correct, so that's okay. Is it possible to solve for y here? Just even you get to this point, is it possible for you to solve for y?
No.
You can factor out y, right? But can I get y by itself? No. So this type of equation, you have to do implicit derivative. So it's not possible. So no. Not possible, right? So not possible. To solve for y by itself. To solve for y. It's not possible to solve for y. So then you say, well, what does this equation look like? Let's try it. I don't know. Well, this is one of them we did last period. Was x, y, what?
Minus
X what?
y
Squared.
Equal to what?
Squared.
So it looks like this. Oh yeah, it's just a problem. It's no big deal. So the last period we did, it was I think to the third power. It looks like this. It's definitely gonna fail a vertical line test, right? So you say, okay, well, so this is math is bad, so bad math, but it just also showed a point that you cannot solve for y by itself. But it's possible to take a derivative of this. This is what am I interesting? Possible to take a derivative, to take dy dx, which is derivative. Okay, so there's a way to do it. Now, who are the founder of calculus?
Leisman? Something like that.
Leibniz.
Leibniz.
I don't know how to say it. Gottfried Leibniz, I think, and Newton, right? I don't know how to pronounce his name. So, but yeah, but this guy is the one that has more contribution of implicit derivative. It's actually much more helpful on many different situations. So he is a very important person, but nobody knows who that is. But he's just as important as Newton. So there are two founders of calculus. One is Newton, one's him. So let's take a derivative of something that's super easy and people just take for granted. So the action of taking derivative is d to the dx. So it's possible to take a d to the dx of x squared. What is d to the dx of x squared? Good, you guys are all awesome. But it turns out there's something invisible that never show.
Y to like goes to 0.
Now, if you look at this as a chain rule, right? If I look at, I'm not looking at as power rule. I'm going to take a derivative of this, right? And then I'm going to take a derivative of x. Derivative of x is what? Just 1, but it's 1 right here, right? So usually there was something here that is also resembled as 1. This is actually dx over dx. Because we take a derivative of x respect to x. Well, take a derivative of x respect to x is 1, but usually not showing. So, not shown. Right? Not shown. It's not shown, then you say, okay, well, why is that important? Because what happens if you take d to the dx of y squared? Pay attention. Again, there are 2 layers, right? So then if I take a derivative of this, it's going to be 2y. Now, this thing pop out. I got to take derivatives y respect to x. So dy dx occur. Do you guys understand? Because I'm taking derivative of y squared first, which is 2y. Now I got to take a derivative of y, but take a derivative of y with respect to x. Right? So that's something that is very, very interesting show up, because this one, people just take it for granted. Never show up. They just write down 2x, so they never see that. But anytime you take a derivative of y with respect to x, you're going to get a dy dx. Building that habit into your brain when you're doing today's problem. Okay, that's very important. Now, what happens if I take a derivative of something like this? Let's say something like d to the dx of x squared y to the third. What do you see here before I do it? What kind of rule I have to engage myself into? Product rule, good. And there is actually a hidden chain rule, because you could take it, the x squared is actually 2x dx over dx, right? Now, there is a hidden chain rule, but we're just gonna just stick with product rule, but anytime you deal with y, you're gonna get dy dx. So if I take a derivative of x squared y to the cube, that is gonna give you 2x. Because I'm just taking a derivative of x squared. I suppose to have a dx over dx, but I'm not writing it. I'm not writing dx over dx because dx over dx is 1. Because that green is kind of light color, it's meant to show you that doesn't have to be there. So 2x times y to the cube plus x squared times 3y squared times dy dx. That was the slope. Am I going too fast? Yes, maybe. No, maybe. Mia, am I going too fast? No? Slow? Devin, am I okay? Huh?
What do you mean by like respect to x?
You gotta speak up.
What do you mean by like in respect to x when you say dx or dx?
D to the dx. That means I'm taking the derivative with respect to x to the expression of x squared y to the third. So the action, I'm taking the derivative. The dy dx is a derivative. The action, if I'm taking derivative with respect to x of x squared y to the third.
So when you write in red dy over dx, are you just like saying that's to represent the derivative of that?
Yeah, this is what we're trying to get. We're trying to get dy dx. Dy dx is the derivative. Okay, so I'm going to go back and show you guys how to clear everything out just in a second. But I'm going to do one more thing though. Let's just say if I take the d to the dx of negative 2x squared y squared, something like that. So for me, if I ever do like a negative 2 that's in the front, the constant in the front, I kind of take it outside. Now, I usually don't write down this step. I just do, what I do is actually just do this. Negative 2, and I just take a derivative of x squared y squared. So it'll be 2x y squared plus x squared times 2y dy dx. Okay, so that's the process I'm taking derivative of. Now, with knowing this 3 things, we have to know one more thing, but that thing's super easy. What's d to the dx of any constant?
0.
Just 0, because if I'm looking at the slope of a constant, that is going to be 0. Okay. So, with that being said, you have all this thing done. You say, okay, let's do this. If I have an expression, let's just say this expression is x squared minus 4x squared y to the third equal to y to the second plus x. Yeah, something like that. And not just say I want to take a derivative of this. I just find dy dx. Dy dx is the derivative. Now, a lot of students always question says, when do I need to know that I need to take implicit derivative? Well, first thing, to give you a clue, there's no possible way to solve y. Another clue that you can see is there's a mixed term between x and y. Okay, x and y. So x squared y to the third, or like y to the third, right? That's usually require you to take a derivative implicitly because explicit is no longer viable. So what I'm going to do is I'm going to take the derivative respect to x. So let's do it together. Let's derivative of x squared respect to x. What am I going to get? It's 2x. Okay, so the negative 4, I'm going to leave it outside like this and then put a parenthesis. That's a very good habit to do. Put a parenthesis, that way you distribute the negative 4. So I'm going to take a derivative of x squared y to the cube. So that's going to be 2x times y to the cube. Does that make sense? Plus x squared times 3y squared And the very, very important thing here, dy dx. Don't forget that because there's a chain rule. Because you're taking derivative of y to the q. It'd be 3y squared, but don't forget the dy dx. Am I going too fast? Now, every time you take a derivative of y, you're going to get dy dx. For example, this one. Derivative of y squared. Hey, I have a y here. I got to do a chain rule, which is dy dx. And then plus 1. Now, what I'm going to do is I'm going to distribute a negative 4. So it's 2x minus 8x y to the third. Am I going too fast? Minus 4 times 3 is 12, x squared, y squared, which is the dy dx. I'm going to use different color. Is equal to 2y and the dy dx. Now, what is interesting is this. I'm gonna get dy dx by itself because the whole goal is I'm looking at what is the changing y over changing of x, which is dy dx, which is derivative I'm looking for. Now, this is the part I'm gonna isolate. So I'm gonna move this to this side, and then move this to this side. Does that make sense or no? I'm gonna get dy dx term by itself. So if I get dy dx term by itself, it's gonna be negative 12. Negative 12 x squared y squared dy dx, and the minus 2y dy dx is equal to 1 minus 2x plus 8xy to the cube. Am I going too fast? I'm just moving all the dy dx term on the left hand side. I factor out the dy dx. So I usually don't even do this step because I can see it in my head. I just divide it over. But I'm going to show you just because this is the first time you see this. It's kind of overwhelming. Now you're going to be like, oh, left for one problem. You don't have to write like, I don't write. I went from the third step all the way to the answer usually, just because I can organize things in my head. I can organize things in my head, so I usually do that. But you don't have to do that. You can do it in your head. But a lot of time people says, why calculus so difficult? It's not difficult. The problem is you guys just don't have the algebra skills. Make sure you practice your algebra skill and get perfected. It's actually pretty easy. Yes.
So I understand the dy dx, like what you're doing. I think it's just my algebra again. What are you doing in the first step that I missed? Like when you got like outside the parentheses 2x minus 4, like what did you do?
Okay, you are talking about this part or underneath?
Yeah,
the first part? Okay, so I take a derivative x squared is equal to 2x. I leave that negative 4 alone. Not just I keep a constant. I just take a parenthesis. I just take a derivative of the x squared y to the cube. And this is a product rule. So because x squared times y to the cube is a product rule, so I'm going to do left d right, right d left. So it's going to be 2x for x squared, and just leave the y to the cube. Are you following me so far?
yeah.
Okay, so now x squared here, I leave that one alone and take a derivative y to the third, so it'll be 3y squared dy dx. And it's equal to 2y dy dx plus 1. The next part is distributing, right?
Yeah.
And then the next part just get dy dx term on the left hand side and then factor out.
Yeah.
Yes, man.
Wouldn't you take the derivative of 1 and get 0?
Oh, no, I didn't. I did take a derivative of x. X is 1. Oh, I thought I messed up, but it was y squared plus x, not y squared plus 1. If I y squared plus 1, if I take a derivative 1, it's going to give me 0. So that's the one thing that people usually screw up too. Does that make sense? Okay. So I'm going to give you one for you to try, and I'm going to see how well you do. Remember, you can create a very good discipline as long as you do it right. So I'm going to say x cubed minus 3x squared y to the second minus y to the minus 2 equal to y to the cube minus 2x. Okay, so I want you to take a derivative of this. Make sure you use that big habit here. Now pay attention. The habit I have that really create us mistake is a -4, and I just put a parenthesis of the product rule. Okay, so once you have that established, then you should be fine. This part of math is to create discipline for yourself. If you discipline, then you do it once and you understand it. Now just keep your sign organized. Julia, you have more questions?
Me?
Yeah.
No, I think I'll be okay.
Once you're done, check your friends, see what they get.
Yeah, I'm gonna watch it.
I will go over it too. Should I go over it or no? Did everybody finish? No? I don't know if you can combine like term though.
Yeah. Okay. Okay. Yeah.
Okay. You done? You confident? Pretty free. Trend, you finished?
What are you gonna say?
Oh, okay. We have it in different order.
If you don't want to look, you don't have to, but I'm just gonna keep going because I don't want to spend too much time. Derivative x cubed equal to 3x squared. I'm leaving that minus 3 alone, and I'm gonna leave something here, so it'll be x squared, so it's 2x. Sorry, 2x y squared plus x squared, and double check my mistake, times 2y dy dx. Take a derivative of negative 2 is 0. It's equal to 3y squared dy dx minus 2. Does everybody have this? Yes.
Does it matter if you have 2y x squared?
What'd you say?
Does it matter if you have 2y x squared?
No, doesn't matter. That's an associative property. Doesn't matter if x times y or y times x or 2. Doesn't matter because I'm going to clean up 2. 3x squared minus 6xy squared minus 6, right? X squared y dy dx is equal to 3y squared dy dx minus 2. Does everybody have that? Okay, so what I'm going to do is I'm going to do it in one step because I can organize things in my head. So actually, let me just do that. Dy dx here, and I'm going to say negative 6x squared y minus 3y squared is equal to negative 2 minus 3x squared plus 6xy squared, and dy dx is equal to negative 2 minus 3x squared plus 6xy squared all over negative 6x squared y minus 3y squared. Did I? Okay. I did okay. How do you guys do?
Did you get that?
Mia, you did okay? Very good. Did anybody did not get it? Raise your hand if you did not get it. It's okay. I'm just gonna make fun of you. No, I'm just kidding. I don't do that to kids. Don't worry. All right. Does that make sense? Okay. Now, what happens? Sometimes I might ask you to find vertical tangent and horizontal tangent. Now, I'm going to show you the easy way to think about it. If I have a dy dx, if you end up with some type of numerator and some type of denominator, like above case, now above the case above is really hard to solve. Sometimes you get, I say, 2x minus 1 on the top. So the numerator of dy dx equal to 0 is where the horizontal tangent. Because the top equal to 0 means dy dx equal to 0. Does that make sense? Now, how about the bottom? Well, denominator of dy dx equal to 0, then it's actually possible vertical tangent. The only thing why I say possible vertical tangent is because sometimes it could be vertical asymptote. So you have to double check with the original function. But other than that, you should know that vertical tangent is a denominator equal to 0 because that's when dy dx is undefined. Something on the 0 on the bottom is undefined. Does that make sense? I'm going to show you how to do trick one.
Yeah.
Mhm.
Extend the last part.
The last part. So the dy dx is the derivative. Now, if the denominator of the derivative is equal to 0, think about it. If you have, let's say, 2x plus 1, and I say 3x minus 2. Now, x equal to 2 over 3 is going to be my possible vertical tangent. Because if it's 2 over 3 here, then that means this part is equal to 0. Now, if some number over 0 on dy dx, that means dy dx is undefined. If it's undefined, then it's a possible vertical tangent. Not entirely always vertical tangent, because sometimes it could be vertical asymptote, but this possible vertical tangent. So you have to check original function to check whether they are asymptote or not. If they are not asymptote, then more likely they are vertical tangent. Almost 99.9% proof. But you have to double check original function. Does that make sense?
Yes.
Okay. Now I'm going to show you some trick questions. So this one is actually one of the question I love to test, is to find derivative of this. Now, some of you guys try to be cute, but please don't try to be cute. First of all, I know half of you guys have this tendency thought that cosine is distributable. It's not. Thank you. The arguments x plus y, they are not distributable. If you want to distribute that, you have to use another thing called sum and difference formula for the CSO, which is cosine, opposite sign, yes, and yeah, something like that. So so if I take a derivative of this, do not distribute become cosine x plus cosine y, and before you take a derivative, that's just really bad math. Do not ever do that. That's just bad math. Now, however, you can take a derivative like there is two things here. So then it's going to be negative sign of x plus y, because inside stay the same, right? And then what else?
Derivative of the inside, x plus y.
Yep, derivative of x plus y is what?
2.
1 plus dy dx.
Oh. Wait.
It's chain.
It's a chain rule.
Yeah.
Because you took the derivative of the y squared.
Oh, okay, yeah. Okay.
Now, what happened here is I'm going to distribute here. Why do I distribute? Because I can't do anything else. The dy dx is inside the parenthesis. I have to distribute it in. So I'm going to get minus sine of x plus y, right? Minus sine of x plus y dy dx equal to 2y dy dx. Now I'm going to get dy dx term on the right hand side, just because this case is much easier because I don't have to deal with negative sign. So I'm going to get dy dx, and I'm going to get 2y plus sine of x plus y. Does that make sense or no? And I hear it's going to be minus sine of x plus y. And I can solve for it. Dy dx is equal to 2 is equal to minus sine of x plus y over 2y plus sine of x plus y. My answer is final. Please do not try to be cute. You know why people try to be cute? They got to this point, they got a right answer, and guess what they try to do? And then I do the same thing on their test. Do not try to be cute. That is done. That's like perfectly done. You cannot get better than that.
You know why you can't cancel?
Well, think about it. If you have 2 over 2 plus 3, can those two cancel to become 1 over 3? That doesn't make sense, right?
Oh, yeah.
The last question, you can watch a video if it's not done properly. But this question is, can you find the second derivative before you ground? It's not as bad as you think. It's just algebra. So I'm going to take the first derivative first. If I take a derivative of x squared, what am I going to get? What's derivative of y squared? dy dx is equal to what?
0, 0.
0. Good. So moving 2x to the other side. Divided over. That's a first derivative. I got a first derivative, pretty easy. Let's go do the second derivative. This part is kind of tricky. I'm going to do it slow. So I'm going to take dy dx of negative x over y. I'm going to do d to the dx. If I do that, I'm going to get d2y dx2. Now, you're going to say, oh, okay, negative x over y. What kind of rule I'm thinking? The quotient rule. Low, d high, minus high, d low. I'm going to write this in different color. This one is going to be dy dx over low low. Is that hard? No, just follow the rules before. What do we know dy dx? Negative x over y. So can I plug in negative x over y? Because we don't want a d2y dx has a dy dx in there. So I'm going to plug in there. So that's equal to negative y plus x times negative x over y squared. Now it's not completely finished yet. Just because this is still a complex fraction. So what we're going to do is combine the fraction on the top. I'm going to multiply this y over y. Shh, pay attention. So I'm going to get y negative y squared minus x squared. Now, since I divide the whole thing by y squared, can I change this to 1 over y squared? Does that make sense? You divide it by y squared, so it would be 1 over y squared.
Why did you multiply by y over y?
Because I need to combine the fraction on the top. The top is like an integer plus a fraction. In order that I need to have a common denominator. It's like 2 plus 1/3. I need to change to 6 over third plus 1 over third. Am I going too fast? It's okay? So that's equal to negative. I'm factoring out negative sign. There's a reason for that. Y squared plus x squared. Hold on, I'm almost finished. Now, the last step is look at the original questions. What do you see? X squared plus y squared is equal to 4. But what do? We have y squared plus x squared. That's also equal to 4. It's a very beautiful answer. And that is the answer that you're going to get. So there you go. One period implicit derivative. We're done. Woo. Homework. Today's the homework. Answer will be provided so you can check whether your derivative is right or wrong. Huh? Yeah, that's on the test, yeah.
Yeah, give it a minute.
Now, later we're going to have to learn how to take a derivative with respect to time, which is a word problem next week. Which is block period, probably already told you, related rate. It's going to be a fun one. But it's going to be interesting though. Julia.
Yeah.